Hello everyone, I am Ma Xian. In this course, I will help you understand the fundamentals of WDM, wavelength division multiplexing. This course focuses on the basic principles, concepts, and advantages of WDM, such as DWDM, CWDM, gray colored light, and C and L bands. I hope this course can help you gain a thorough understanding of the basic principles of WDM and its related concepts. Light not only illuminates, but also transmits information. Light travels through the air at 300,000 kilometers per second and reaches the speed of 200,000 kilometers per second in optical fibers. It is the best carrier for fast information transmission. The way light carries information is similar to radio, quickly transmitting voice, video, and other data. Yet, with the WDM technology, the speed can be increased exponentially. How exactly does WDM achieve that? Let's take a look at this optical phenomenon. When a beam of white light travels through a prism, it divides into 7 different colored beams. When these colored beams of light travel through another prism, they merge back into a single beam of white light. From this, we can postulate that light is further divisible. Indeed, a single colored beam of light can be further divided into wavelengths. Let's take a look at a real WDM model. The light in an optical fiber is composed of multiple wavelengths, each of which can carry different information. Therefore, the volume of information being carried will be substantially higher than a single beam of light. If a WDM system contains 80 wavelengths, then the volume of information will be 80 times that of a single wavelength. Let's make things easier to understand by comparing the WDM system to a traffic system. A single light is like a single traffic lane. WDM aims to put multiple wavelengths into one optical fiber and achieve multiple lanes. Even at the same driving speed, the WDM system can deliver several times more goods. WDM also achieves low-cost and ultra-long-haul transmission. Ordinary communication technologies such as SDH, routers, and switches are limited by distance. Using the traffic analogy, this would mean a new car is needed for every 80 or 100 kilometers driven, sharply increasing costs. However, the WDM system can fuel multiple cars simultaneously after certain distances, meaning the cars are able to last thousands of kilometers without changing. Now that we've been introduced to the principles and advantages of WDM, let's further explore a few concepts. WDM can be categorized into dense wave division multiplexing, DWDM, and coarse wave division multiplexing, CWDM, based on the channel spacing between wavelengths. Channel spacing in a DWDM system can be as small as 0.8 nanometers, 0.4 nanometers, or even 0.2 nanometers. A CWDM system has relatively larger channel spacing, generally 20 nanometers. Let's move on to gray light and colored light. Gray light, also called white light, has a broad wavelength range and usually occupies an optical fiber on its own. The center wavelength can be 850 nanometers, 1,310 nanometers, or 1,550 nanometers. Colored light refers to light within a specific wavelength. The wavelength range is narrow and can share one optical fiber with other colored light. The wavelengths used in both DWDM and CWDM systems are colored light. Finally, we've come to C-band and L-band. Light undergoes certain losses while traveling through optical fibers. Different bands have different losses, with the C-band and L-band having the lowest losses among all the bands. The C-band in particular has the lowest loss and is widely used in WDM systems. The wavelengths in the C-band range from 1,530 nanometers to 1,565 nanometers and are called normal wavelengths. The wavelengths in the L-band range from 1,565 nanometers to 1,625 nanometers and are called long wavelengths. To recap, I've introduced the basic principles and advantages of WDM, as well as a few basic concepts such as gray and colored light and C and L bands. Is everything clear so far?